Okay, so.
Sorry, I will start recording now. So go on.
Okay, I have to click here, I guess. Good. Hello, so good morning, everybody. Thank you very much for being here again for this Severo Ochoa colloquium. We are in person in the conference room at the IAS, which is a pleasure always. We have today the honor, the pleasure and the honor of having here Professor Michael Edmonds, who is the actual president of the Royal Astronomical Society since May for the next 2 years. So thank you very much, first of all, Mike, for being here with us. It's really a pleasure and an honor that we have. Professor Mike Edmonds is Emeritus Professor of Astrophysics at Cardiff University and former head of the School of Physics and Astronomy. He has been recently elected, as I've said, as president of the Royal Astronomical Society. He received here his undergraduate degree and his doctorate from the University of Cambridge, but he has lived and worked in Wales for over 35 years. His research career involved the determination and interpretation of the abundances of chemical elements in the universe and the investigation of the origin of interstellar dust. And later work has been in the early history of the Royal Astronomical Society and the history of astronomy. He has served on many committees and panels of the UK Research Councils, the Royal Astronomical Society and the Institute of Physics, and he was formerly a member of the Particle Physics and Astronomy Research Council. He is vice president of the Herschel Society, and which has a connection with music, so I love, we have to talk together, and honorary vice president of the Society of History of Astronomy. He heads the Antikythera Mechanism Research Project, did I say it right? Antikythera Mechanism Research Project, which is an international collaboration investigating the extraordinary astronomical machine dating from around the 200 before Christ, discovered by sponge divers over a century ago off the Greek island of Antikythera. And he has occasionally been seen in his one-May play about Newton, which is called Sir Isaac Remembers, that extremely interested in watching somewhere. So today he's talking about the Antikythera mechanism and the mechanical universe. Thanks a lot, Professor Edmonds, and the floor is yours, and the micro as well.
Thank you very much for your very warm introduction. It is delightful to be here in Granada and visiting Pepe. You can see what he thinks of my lectures. He's just left. I expect he will be back. But it's wonderful to be back here. I've visited the city several times, but I don't think I've visited the Institute before. And it's lovely to catch up with a lot of old friends who I haven't seen for many years too. I want to talk to you today about the Antikythera mechanism, this extraordinary relic from early astronomy. I didn't start off as a historian of science at all. I've been a working astronomer all my life. That's what I think I'm known for on the whole. But as you get older, as my wife said, you become more part of history. And perhaps that's why you become more interested in it. And I must say, I've had great fun sort of moving across fields for a while into the history of astronomy and finding it fascinating in its own way. What I'm going to try and do is to take you back to Greece, to Hellenistic Greece. We're around the time of maybe 100 BC, as you mentioned vaguely in your introduction, around 100 BC before Christ, something like that. The Greeks are still around. It's not a bad place to live in Greece, but the Romans are coming. The Romans are conquering all around the Mediterranean. I believe in Spain, you knew about this at some time, probably not long after, if not at the same time. And there's no doubt the world is changing. The world is changing from the Greek into the Roman Empire, and that's what's happening. But it's a time of transition, a slightly, no, I won't say dark age, but a sort of age between the golden days of Greece, which were perhaps 300 years ago, if we were then, and what's going to be the glory of Rome, if you can call it glory. It depends how you look at these things. which is going to be in about 100 years. I think the empire is going to be proclaimed in about 50 years' time, something like that. We're in that sort of slot. And from that time, it was, as you know, a time of great learning. And from that time comes this extraordinary device. It's called the Antikythera Mechanism because, as I'll show you, it was found in a shipwreck by the island of Antikythera. That's the reason for the name. The shipwreck was around 70 to 60 BC. The shipwreck is dated quite well because of coins and things found on the wreck. I'll show some of the other stuff found on the wreck in a minute. But there's no doubt, it's within 6 years, I would reckon, of 60 BC, this wreck, which is not bad for archaeological dating, I think. It's fairly good. Easier than dating galaxies. Anyway. Where the mechanism was made and when remains something of a speculation. My own best guess, and it is no more than the best guess, would be that it was made probably in Rhodes, on the island of Rhodes, somewhere between 140 and 80 BC. That's my guess. It could have been made earlier. Some workers say it's earlier than that, but that's my personal preferred timescale. Anyway, it's within 100 years of that. That's the timescale we're talking about. Now, where is Antikythera? Well, down here in Spain, you probably know much more about the Mediterranean than we do up in Wales. You know, we hear about it, but we worry about these sea monsters and things that apparently inhabit the Mediterranean. Here's Crete, down here on this map I'm showing. Rhodes is over here to the right. Athens is up here. And here is Kythera, the island of Kythera off the Peloponnese, and just across the strait from Kythera is the island of Antikythera, across from Kythera, basically. That's where the name comes from. And it's there that a shipwreck was discovered, as you mentioned, in around 1900, so just over 120 years ago now. A shipwreck was discovered by sponge divers. And in subsequent, what happened was apparently one of them dived down. The sponge divers, they were going over to North Africa, which is where they normally collected sponges, but they got caught in a storm and they'd sheltered by the island of Antikythera until the storm blew itself out. And then they dived, I presume, to find sponges or perhaps some lunch, I don't know. Anyway, after a few minutes, one of the divers is said to have come up with a bronze arm in his hand saying, there is a shipload of young ladies down there. Well, when they had calmed him down, what these were, he'd brought up an arm of a statue, basically, and there were other statues and things there. After this, the first main archaeological underwater expedition that there'd been was mounted over 1901, 1902, involving the Greek Navy, the Greek state, and the National Archaeological Museum in Athens. And they went to the bottom, brought up what they could, took it back to Athens, and tried to sort it all out. Now, in this shipwreck, there were various things. Here's a picture of one of the ships which was working, or boats which was working on the recovery. Can you see this thing? I'm pointing on the left here at the bottom to a sort of rather gnarled looking old rubbishy object in the bottom left on this picture. And if I clean that up, it's that, an absolutely magnificent statue. Bronze statue. This was in the shipwreck. There were other very fine works of art. There were marbles, like this horse's head. There was also some very fine glassware. This beautiful glassware I'm showing, which the top right-hand one, looks as though it could have been made in Paris or something in 1920s, doesn't it? And that is, however, must have been made before 60 BC. Superb craftsmanship, superb archaeological remains. But the thing that interests us is a lump of bronze, probably something about this sort of size. There are various conflicting reports of how it got back onto the ship and into Athens. But basically, this lump of bronze got back into the Athens Museum. It probably dried out and cracked a bit open. That's my guess. OK. And an ex-minister of the government was walking around the museum and he said, "What's that?" And they said, "Well, it's a lump of bronze," or words to that effect, I expect. He said, "Well, why has it got gear wheels in it?" Because he could see where it had cracked and he could see there were gear wheels. And if you notice here, this is the main fragment that is left. The whole thing is in many fragments. I'll show a picture in a minute. But if you can see here, this is the main fragment, and this beautiful wheel here, which I will call the chariot wheel. I think you know why I'm calling it the chariot wheel, because it looks like a chariot wheel, though it has, well, perhaps it has something to do with chariots, which I'll talk about later. Anyway, that itself is a gear wheel. There are also other gear wheels. You can just see them, evidence of the gears. You can see just some evidence of the teeth. You'll see those better in a minute. Now, this was unusual because metal gear wheels, this is bronze, were not known from the classical era. So straight away, this was an extraordinary object because it had gear wheels in it. The other thing is that it had inscriptions on it too. And I'll describe those in much more detail as we go through. And the inscriptions very quickly indicated that this thing had some sort of astronomical function. Things got really exciting about 60 years later, when the first radiographs of the mechanism were taken, which allowed people to see inside the lumps that were remaining. And that was done by a Greek guy called Karakalos, together with an American-English physicist called Derek de Stoller Price. And once they got these X-rays, started doing the X-rays, they realized that in these lumps, not only were there gear wheels, there were at least 30 gear wheels. Now, 30 gear wheels is quite a lot, particularly if you didn't think that anybody made gear wheels in those days. And of course, then the interest to know was, well, what on earth was this object and what did it do? Here's a picture showing some of the remaining fragments. I think at the last count, it was 82, probably about 85 now. Somebody's probably dropped one or two of them. And some of them may or may not come from the actual mechanism. They're in a drawer in the Athens Museum, some of these. Anyway, the main fragments, there's a big fragment. There's about 6 main fragments, which it's really about those that I'll be talking, that you can get the information to piece together what this thing looked like. I've shown you one fragment with the chariot wheel on. Here's another fragment, the second largest really. Now this is fascinating. If you can see this fragment, it looks like a semicircle, really, but with parallel or sort of, what would you call them, circles, parallel circles on it, or annually around it. And as we'll see, indeed, these are annually. You can see that there are also slots between the annulus. They're a bit gummed up here, but those are slots between the annuli and the bronze. And these are the first known scientific scales, or, you know, these are going to have indicators on them. They're marked. They're things that move around to show you things on these dials. Here's a third fragment, and this is a small fragment. It's been blown up cruelly. The actual fragment itself is, I'm just indicating with my hands, it's just a small piece of bronze. And you can see several things here. First of all, you can actually see one of the scientific scales, quite nicely divided. I think you'll see the scale divisions there with writing on of various kinds. The other thing is, you'll notice that the faceplate here is bronze, okay? And this bronze faceplate is covered with Greek inscription. Now, this is fantastic because not only is this device got all these gear wheels we can investigate, but it has all these inscriptions in Greek, which I suppose you would expect. I would have got a bit worried if there were any other language, I suppose. Which can be translated and one can try and find out about it. Unfortunately, it is not an instruction book. I don't know quite how to describe. I'll tell you some of the things that are in it later. But it's more like, you know, you get a new mobile phone and you take out, and there's a thing that tells you what frequencies it uses and how it's better than anything else, and you know you should connect it to Bluetooth or something or other, but really doesn't tell you anything apart from a lot of figures and things. So it doesn't tell you how to turn the damn thing on, but you have to learn that other ways. It's a bit like that. It's a specification document really, rather than a true instruction document. Okay, well, I got into this business around the year 2000. I had a research student, an undergraduate student, who wanted to do a final year project in something fairly practical. He was an interesting student because he, in fact, before he came to our university to do a master's in physics, he in fact had earned his living by making wooden furniture. So I thought, yes, good thing to do when you're getting older, to go and do an astrophysics degree, which is what he did. He wanted to do something practical, and I happened to see an illustration in a book of the Antikythera mechanism. And this rung a bell. I must have seen this, oh, I don't know, 20 years before, 30 years before or something. I remember seeing this picture. I thought, well, what is that thing? I said, well, look, you want something practical to do. Why don't we find out what we can about this Antikythera mechanism? So he spent the year with me. We just tried to dig up everything we knew, could find about the Antikythera mechanism. He was a very good student. He did some computer simulations and various other things. And in the end, we published at the end of the year, we published a joint paper reviewing what was known about the device. That got me really interested. I started talking to various other people who also got very interested in this mechanism. In particular, a guy called Anthony Freeth, who was a mathematician and filmmaker. And also we got together to set up an international project to try and find out once and for all what this thing was. What we realized that in order to be able to understand it, we had to get new data. We had to get state-of-the-art, basically X-ray tomography or body scan of the fragments to see what actually was in there. And we had to obviously work with the Greeks. We worked with some wonderful Greek collaborators, particularly I'll mention Xenophon Mousas, Yanis Pitsakis, and John Seridakis, who I know some of you know from radio astronomy. He alas died a year or so ago. Lovely, lovely man. And we set up an international research project involving the Greeks, some Americans, and some British. And this collaboration worked very hard for about 2 or 3 years, and then subsequently less hard, but carrying on the work. And we got a grant from the Leverhulme Trust to enable us to do the experimental work, fortunately. So it's really the result of not my work, but all this lot, that what I'm telling you today is known. We took an X-ray machine that we borrowed down to Athens. We had to put it on a lorry, drive it down through Europe, through the streets of Athens in the early morning, and into the basement of the museum in Athens. As you can see, it's quite a tight squeeze, but we had measured it. Honestly, we had measured it, and we knew it would. It would have been much easier for me to take a briefcase and go and put the pieces in my briefcase and just take them back to the X-ray machine in Britain. But no, the bits of the Antikythera mechanism cannot leave the museum. And this is quite right. It is so valuable, so unique, that it's better that it's carefully protected and stored. So anyway, we did that, and it worked, fortunately. And here's one of the pictures. I'm not going to show you lots of radiographs. They're fascinating to those who they're fascinating. It gets a bit boring otherwise. I could show you some of my liver as well, probably, but no, never mind. Here's a sort of shot through the thing. Can you see a bit better? It's just the main fragment. Can you see that those sort of scales there? I'm iterating these semicircles here. Here's the main chariot wheel. You can see that. And you can see lots and lots of gears and spacers and bits and pieces inside. And basically, this new data set, a sort of three-dimensional cube, because we could slice through in 3 dimensions, is really what allowed us to find out what was going on. The first thing I wanted to do was find out what the counts on the gears were. Because if you can work out what the counts on the gear teeth are, you can begin to work out how the mechanism might have worked and what it actually did. And here's a typical gear. You can do measuring by measuring the teeth. It's a little bit of a messy process. We developed some statistical estimators, so you could get maybe for a typical gear you'd get a count either 1 or ±2, something like that. A lot of them we had enough teeth to be able to say yes, it's this many. And here are the counts if you're interested on the gear wheels that still remain. That's what they are. Some interesting numbers there if you're mathematically inclined. 53, 63. Why make a gear of 63 and 53? Interesting. Some of these are much easier to divide. You can think of making these gears. Some of these sort of even numbers are going to be much easier to do. 127 is an unusual number, but that was known if you're going to do anything to do with the moon and the cycles of the moon's behavior, 127 comes in. So, that was already known before we started, that there must be something to do with the moon here. And you can see there's a 223 here. We'll come back to 223, but some of you, I hope, already are thinking, that's an interesting number. I know that number. Anyway, so how did the thing work? I'm going to cut this story short because otherwise I'll go on all day. And Pepe says I'm not allowed to go on over 4 hours. Oh, no, that was 1 hour, wasn't it? Anyway, I'm going to show you a picture. It's a box. This thing comes in a box when it was original, about the size of a shoe box, you know, box you get shoes in, right? And it has a front face and a back face. And there's going to be gearing inside. And then there are doors, or some kind like a door, on the front and on the back. And there are inscriptions on those doors. There are inscriptions on the front and back plates. And there's gearing inside. I'm just going to, once this has been disentangled, I'll describe what happens, okay? I won't try and tell you how we disentangled it. What you see in this picture I'm showing is a picture of the gearing, which is quite complicated, as you can see. Can you see here the main chariot wheel? Okay. Now, the whole thing is based on the following sort of basic cycle. One turn of that wheel is 1 year. Turn that wheel once, and that's 1 year of time. You can turn it by a handle or something similar on the side to a little crown wheel, you know, a crown gear wheel that's sort of flat with teeth sticking up. Looks like that if it's a gear wheel. There's the other gear. I'm trying to, you get the idea, you can do it yourself afterwards. Okay, turn it on the side. One turn of that is gives you a year. And what this is going to do, there are various gear trains here that feed to the front dials, which we'll look at in a minute, which show the position of the sun and the moon in the zodiac. And the back dials here, which give calendrical functions. There are all sorts of calendrical things that we're going to talk about that are displayed on the back of the thing. Okay, and these complicated gear changes, I'll describe how they work in a minute. You can see there are three gears in green here. Those aren't there in the actual mechanism. They've been broken off. You can actually see on some of them that they have broken off the shaft, right? And we've put these in. If you ask for the right size to fit in there, it's the right number of teeth to do what we think it's doing. Everybody now accepts, I think, that slight reconstruction is fine. More detailed reconstructions, which I'll talk about later, beyond this, that's more controversial, but this is now pretty well accepted as what's going on for the basic mechanism. So it would look something like that. There's the front. It's got annular dials around here. That's got the signs of the zodiac around and a calendar, just a day calendar, essentially the Egyptian day calendar of 365 days. There was a pointer to show where the sun was in the sky and a pointer to show where the moon was. And also, interestingly too, a half-colored ball, half black, half white, that would turn to show what the lunar phase is. I'm sure you've seen these in later clocks. Leonardo da Vinci invented this. But he wasn't the first, okay? In fact, this device dates back to the mechanism, which, as I say, is around 100 BC, okay? And probably almost certainly on the front here, at least it was intended that on the front here, also were displayed the positions of the planets in the sky, the known planets then, because only 5 were known then: Mars, Jupiter, Saturn, Mercury, and he's awake. Venus, good. Okay, just checking. Okay, and the 5 available. There is some controversy about exactly how this was done and why the mechanism for this particular part, the planetary mechanism, is missing from this, but we'll talk more about that later. Another thing that we benefited from in working all this out was some special surface imaging techniques, where these are optical surface techniques due to a guy called Tom Maltzbender from California. He had this very clever device which has multiple flash bulbs, a camera, some smart software, and it then allows you to take a surface and re-illuminate it from all different directions and do image processing. To show you the sort of thing it can do, here's one of the fragments, which we call the Isle of Wight fragment. From Spain, you may not know the Isle of Wight in Britain, so I don't know, perhaps the Kos fragment or something, I don't know. Anyway, our Isle of Wight fragment, you do the image processing on that, and that pops out, as you can see. Now, this is great. This part of the thing was known before we started, but it hadn't been really assessed in great detail. If I zoom in on that, you will see that there are 3 numbers there: 76, 19, and 223. Right, now, being astronomers as you are, you will immediately recognize the significance of these numbers, won't you? It's amazing how many audiences of very distinguished and well-known astronomers begin to look at the ceiling at this point in these talks. Had you been an astronomer in the classical age, and even if perhaps in Victorian or before times, you would have recognized these numbers, but obviously today we don't so much. Let me go through them. 19. 19 is the number of years in the metonic cycle, okay, from meton, a Greek astronomer. Now, let me explain that cycle to you because it's quite an interesting one. You know that the number of lunar months in a year isn't integer. Yeah, it's a real shame because it'd be much easier if we could do that, because then you'd know when full moon's going to be, new moon. You could organize your barbecues much more easily. In classical times, it would have been important for civil ceremonies, religious ceremonies, etc., to know when new moon and full moon were going to be. Now, the metonic cycle is a very clever cycle. What's the date today? 2nd of June. 2nd of June. What's the lunar phase tonight? It's just crescent. That's right. It's just off full moon, off new moon. It's just becoming a crescent, just going towards first quarter, but it's a crescent moon, right? You come back here in 19 years on the 2nd of June, and it'll be a crescent moon again. Okay, that's a really useful cycle. If you know that, you can work out all the new and full moons in between. Okay, that's the metonic cycle. 76, right? Well, that in fact is the Calippic cycle, after Calipos, whoever Calipos was. After Calipos, that's 3 metonic cycles minus 1 day, because that's even more accurate. You may not want to use this a lot, but it's useful to know. And it's interesting that they were accurate enough to know that, okay? Now, what about 223? Anybody recognize it? Lunar months it is. It's the number of lunar months in a Saros cycle of eclipses. If you have an eclipse occurring at either new or full moon, which is the only time they can occur, and also they can only occur when you're near the lunar nodes, but we'll not worry about that for the moment. If you have an eclipse, say we'd had an eclipse at this new moon now. In 223 lunar months later, there will be a very similar lunar eclipse, but shifted in time by 8 hours. Okay, same thing happens with solar eclipses. So if you draw up a table of eclipses in the past, you can use this cycle to predict when you'll get eclipses in the future. Okay, and that's the Saros cycle, and we'll come back to that in a minute or two. Now, when we first started doing these investigations, one of the first Greek things we read was a spiral divided into 235 sections. Where have you heard 235? You heard it a moment or two ago. The number of months in a metonic cycle is 235, okay? So this implied that some spiral here, is divided into 235 sections. Well, if it's 235, it must be the metonic cycle that they're doing. And indeed, that's absolutely right. This fragment here, with this sort of dial with these slots in, indeed was a metonic cycle dial. And it's at the top of the back. It's a 1, 2, 3, 4, 5-turn spiral, incorporating 235 divisions. So there's a pointer, and I'll just talk about that again in a minute. So what this dial is going to tell you is where you are in the metonic cycle as you turn the knob. I'll come back to the bottom. This is a 4-turn spiral at the bottom. You may be already guessing what it might show. Anyway, let's just look at the top one for a minute. 235 elements. It would look something like this. There it is at the top, and there it is at the bottom. Now, you remember I said that there's a slot cut in to the bronze around the spiral. Now, how do you show where you're supposed to be looking on a dial like this? Well, it was very clever. What they did was they had a little shaft that came out through the middle that turned, turning a pointer, and the pointer itself had a pin on the end that fitted in the slot. And the pointer could pull out, in and out of the central, pivot, okay? So you put the thing in, you wind round, and it pulls the thing across the dial as you go around. Do you remember like the old vinyl records? very much like an old vinyl gramophone record. So all you have to do is look at the end of the pointer, and that's where you're supposed to be. And when you get to the end of the cycle, you just unplug it and put it back at the beginning. So it's a very nice little bit of device to display a complicated cycle. These cycles came to the Greeks from the Babylonians. They were known about in Greek times by the transmission from the Babylonian culture. And the Babylonians did an awful lot of work just simply observing and recording what they saw on clay tablets. There are thousands of these things. I expect you've got some in the museum here if you go looking. On clay tablets, which deal with lunar, solar, planetary cycles and so on. That information was carried over from the Babylonians and incorporated into this mechanism. And there's a sort of rough diagram of this pointer. You can see the thing that fits in the slot, and it slides in and out here, and the central pivot there. Now, this is what drives that dial at the top there. You turn the handle at the side here, it turns our great friend the chariot wheel, and the gearing goes down through here and turns this, so that as you turn this, one rotation of this for each year, this goes round in 19 years. Now, interestingly enough, there's a little bit of gearing to a subsidiary dial here, a little small dial, a quarter dial, as I'd call it. There it is. There's a picture of the actual thing, and with care, you can see various names around here. Can you read these? They are Greek, but they're not that difficult. What does that say? Nemea. Okay, you may not know what Nemea is, but you know what this is. Olympia. These are the Pan-Hellenic Athletic Games. It has a little dial on it that tells you what Olympic Games or Isthmian Games or what other games are being held that year. What on earth is that doing, you're saying, on an astronomical instrument? Well, I suppose it's a useful reminder to book your tickets, but apart from that, it's a way of knowing where you are in the calendar, because calendars varied all over the place across the Mediterranean. All different cities, different states would have different calendars and different calibrations and so on. But probably everybody knew at least which games was being done that year. So I think that's what this is. It's an orientation dial, because it tells, well, that's the year on which you'd expect the Olympic Games. Oh, yes, that will be the year after next. I think that's what this is probably here for. And interestingly enough, when we were working hard on the inscriptions, we find in the end also there's another name here, which is Helleia, I hope I've pronounced that right, which is a very small games that takes place on the island of Rhodes. And that's one of the reasons why I think this may have been made in Rhodes, because this wasn't a particularly well-known games, but it would have been, you know, if somebody in Rhodes made this, they might put it on as a sort of, yeah, keep up the tradition, lads. Okay. So, what's the lower back dial? Well, the lower back dial is a double spiral, a four-turn spiral, and it has these what we call glyphs on, a bit like hieroglyphs. Took us a while to work out what these are. I thought this was a symbol for the sun. Being a good astrophysicist, it isn't. It's 9 or something. The sun is H here for Helios, and sigma for Selene, of course, with the moon. Okay. And what these do is these say if the pointer comes over one of these, it says there's likely to be an eclipse that month. Okay, and that's done presumably from a tabulation they had of previous eclipses, worked out when there might be a next eclipse, and they're then tabulated around this dial. And interesting enough too, that there's also a little subsidiary dial with 3 parts in, geared, which is an exeligmos dial. The exeligmos is 3 Saros cycles. Now, do you remember I said it shifts by 8 hours? So this goes, it tells you either it's this cycle or shift 8 hours, shift 8 hours, shift 8 hours, and you're back again. So it allows you to cover 3 Saros cycles. Just says to add 8 hours onto the time, add 8 hours onto the time, or 16 hours onto the time. And here's the gearing for that. There's, from a different viewpoint, there's our chariot wheel. You drive that, it goes down through this, through this, through this, through this, and it drives the main wheel there and the little subsidiary exeligmos dial. Now, looking at this, you may think it looks a little complicated. And one of the things when we first did this was we noticed that there were these 2 big gears in here, E3 and E4, And we said, well, the Greeks aren't very bright, are they? I mean, you could have done this much more easily with smaller gears. Big mistake. Never underestimate the Greeks, especially those bearing gifts. Okay? You'll see in a minute that this isn't a silly design using extra material. It's a brilliant, brilliant design, as we'll see. But that's the stuff that leads down to those back dials. Okay, that's just a picture of what they would look like. Now, shortly before we started work, a guy called Michael Wright, who I think I've got a picture of here. There he is, Michael Wright, who has worked at the Science Museum in London, has done a lot of very, very good work on the Antikythera mechanism. He had noticed that the gears, some gears on that main fragment, which I showed you, one of them, there are a pair of gears, and one of them has a slot in it. I don't know if you can see there. It's just there's one gear, there's the other gear, and there's a slot in the gear, right? Now, there's a blow up of it, so you can see it more clearly. Here's the slot, and there's the pin in the slot. You can see the teeth there. Now, what's going on here? Well, I'll show you in a minute that the thing showed on the front. I mentioned that it showed the position of the moon in the sky and the position of the sun in the sky. Now, let me ask a question. When the moon, you go out each night and you observe the moon, right? This is going to be your homework for the next week or so. Goes each night, do you notice that the moon has moved? Hopefully. Does it move the same distance every night? No, you're safe, aren't you? Because I wouldn't have asked otherwise. Okay. No, it doesn't. It varies slightly. And we know that why that is because the moon has an elliptical orbit. So sometimes it's moving slightly faster, sometimes slightly slower. Now, what this mechanism does, and I'll show it in a minute, is in fact put that slight variation of motion into the lunar drive so that it follows this slight variation in motion of the moon. And it does it, if you imagine the gears are configured like this, the input is the yellow, so this wheel turns on the drive, that turns this wheel here that has a pin on it that pushes on the slot in the gear above it, which turns another gear, which then goes off to drive the pointer, as you'll see on the front dial. Okay, now, what happens? Well, you'll notice that these two gears are mounted slightly off axis. So sometimes that pin is pushing far away from the center, and sometimes it's a little bit closer to the center. Can you see what will happen if you do that drive? You'll get a sinusoidal, quasi-sinusoidal drive through. That is just of the right amplitude to do this lunar anomaly. And so this is how, there's the full gear train. Our old friend turned the chariot wheel, the gears come down through here, it drives this variable speed device of 4 gears here, and then feeds back, and feeds out to the lunar indicator on the front. It's quite complicated, isn't it? Now, remember I said about those big gears? You'll notice that these little gears that do the variable speed are mounted on those big gears. The reason is that that big gear turns in the machine thing about every 8 years or so, in the 1-year turn of the main. Anybody remember that strike any chord? The precession of the lunar orbit. The lunar orbit precesses slightly, which means that the variation in this lunar anomaly is not at quite the same period as the actual lunar orbit itself. There's a slight difference in period. By mounting these gears on those other gears, the thing reproduces that anomaly and at the right period, not the ordinary lunar period, but this slightly varying lunar period. That's astonishing, isn't it? Okay, they've not only got the anomaly, they've got the period right by epicyclically, and this is amazing design. We had no idea that the Greeks could do that kind of design, mechanical design. Okay, there's the full gearing. Wonderful. There's this is John Sorodakis insisted on having this drawing, which is, it done in modern, follow that through as a mechanical engineer if you wish. Yeah, make one for me later, all right? Okay, so what's important about this mechanism? It's based on Babylonian period relations. The astronomy in it, what's in there, this anomaly of the moon, all the other stuff that's in there, the ecliptic cycle, you know, the cycles and so on, is exactly right for around 140, 100 BC. Now that's good because it means there's not something in here that's you know, that it hasn't got the orbit for Pluto in there. If we had, we'd have been a little suspicious. Okay, but it's just right. The astronomy is just right for the time. The design is superb. We had no idea that they designed stuff like this. And as I'll talk about in a minute, there are various literary accounts of such devices. But I think you wouldn't, if you'd seen something in a literature saying, look, we have this device that shows the planets in the sky and so on, you'd say, yeah, of course you do. You know, but they did. Okay. If you're interested in following up more, there's a nice book published by Oxford University Press called The Portable Cosmos by my colleague Alexander Jones. That's very good. And if you just want a quick resume, in Nature Astronomy in 2018, there's a short article about what we know at present about the mechanism. Okay, how am I doing for time, Pepe? 10 minutes. Okay, I'll have to rush a little bit. 10 to 12. Okay. This is a diagram. Where would you say this was of? Manhattan? This is, in fact, Rhodes around the time we're talking about. It was a very military city, high technology, a bronze casting industry. And it's here, as I say, that I think the thing was probably made. Also, from that time, we have jewelry, beautiful jewelry. You can see they were wonderful technicians. They could build beautiful things. What we didn't know is they had this mechanical design stuff as well. There's a picture of the exploded case of the box. As I say, there's the front dials, there's the back dials, and there are the two doors. And where the shaded areas are where the inscriptions are. And if you're interested in the inscriptions, a whole volume of the journal Almagest is devoted to those inscriptions. When we started working, I think about 900 characters in Greek were known when we'd finished over 2,500. So it's really a newly discovered astronomical text, essentially. So what do we learn from the inscriptions? Well, first thing we know that they definitely showed the planets. It was intended to show the planets. And I think I've got a picture here of that. Yes, here we are. Here's a picture of one of the X-rays. You see it's rather ghostly, but that talks about the moon, that talks about Mercury, that talks about Venus, the sun, Mars, Jupiter, and Saturn. Now, if you notice that, that's just the sort of order that you would expect going out from the Earth in the geocentric view of the time. And there are various data given on the inscriptions implying that there was this display on the front of the planets. The texts that are on the mechanism about things like equinoxes, solstices, and so on, they're very similar to the book Geminos. I don't know how many of you know Geminos's Introduction to the Phenomena, which was written around 50 BC. They're very, very close. It's another reason why we fixed the period. The writing's very, very similar. And what's stated is very, very similar. So it's a sort of all very consistent. The engravings had at least two engravers working on it. They're in different hands. There's just a hint of astrology in the mention of the color of eclipses, but I'm not going to talk about that now. Okay, here's a sort of modern reconstruction of the thing with all and planetary mechanisms and goodness knows what. Now, I'm going to be not rude about reconstructions of the planetary mechanism, just a little careful. There are various reconstructions have been done. I've done some myself and so on, of how the planets might have been represented on this, because that bit of the mechanism is missing. Apart from there's a 63-tooth gear that we can't fit in. It's like one of those IKEA flat packs. Do you make these furniture? You have IKEA in Spain, don't you? Yeah. There's always a bit left over at the end, isn't there? Which you don't know where it went. Well, that's the same. There's a gear. So we don't know where it went. Could have been part of a planetary mechanism. We're not sure. But as I say, that bit's missing. And so you can have wonderful fun speculating how the planetary mechanism worked to show the planets and their retrogrades. It almost certainly showed their retrogrades. It's not just a simple mean period. It showed the retrogrades. So that you can have great fun doing that. And many people have fun doing that. I don't think it matters in detail how that's reconstructed. We know from the way they did that lunar mechanism that they could have done the planetary mechanisms. They had all the techniques to do that. They had the mechanics to do that, and they had the information to do it. So we know they could have done it, and that to me is far more important than whether they did which particular way they did it. That's the important thing. But it's fun to speculate, and it would be lovely to find a mechanism so we find out how exactly they did it, but I don't necessarily think it's of the first importance. I did some work asking how accurate this device is, and you can do that. I did some simulations looking at these. They're just bronze cut, the gear wheels are bronze discs cut with a file to give you the teeth. You can then work out what the errors in that are, and you can do simulations to work out, therefore, how accurate the predictions of the machine would have been. As well as weight, it depends on the models you're using, but you can do that. And basically, you can find, in fact, if you looked at the lunar train as time went on, the position of the moon would typically be a few degrees out, but sometimes it would be 10 degrees out, sometimes it would be 20 degrees out. So don't use this mechanism for predicting when new moon is, because you might be a day or 2 days out. But apart from that, it's because it's geared up to do the moon, basically. All the calendrical stuff at the back is accurate. In other words, these errors in the gears will give you the correct month almost always. Not absolutely always, but pretty much always. It'll tell you whether there's going to be an eclipse that month or not. It will work pretty well. It's just in the lunar train, it would have been more difficult. Okay, so 5 more minutes. Okay, 5 minutes. My conjecture is this. This is a spheroi. This is what the Greeks would have called a spheroi, this mechanism. That means other things as well in Greek astronomy. But my conjecture is that these mechanisms were known about during the period 250 BC to 500 AD, and were a major influence on the development of philosophy in antiquity. The idea of a mechanical universe. You see this thing working. Does the universe work like that? I know the universe hasn't got gear wheels as far as we know, but there's something. Can you explain the universe without having to have gods pushing the planets around? And okay, you don't know what the exact mechanism is, but the fact that you could make something that mimics this and does exactly the same thing is surely very important in your philosophy. I rather like to illustrate it with this. This is my fridge magnet at home. Okay, now this mechanism is causal. You turn the thing, things happen. It's deterministic. You do the same thing twice, you get the same thing at the end twice. It's regular. Okay, like a lot of the universe is regular. There's also regular irregularity. Okay, that's in there. And also, which might or might not be important, there's a single prime mover. You just turn one thing and all the things move. Now, that to me is a mechanical universe to some extent. Of course, it doesn't mean everybody accepted that. That certainly would have been disputed and was disputed, but that's really what was going on. But the fridge magnet here, I'll just play it for fun, just to remind you. So this shows everything. You see, it's got the regular motion and it's got the regular irregularity. But one's getting quite scientific in a way, I suppose. I don't know if that's the right word, but looking at the universe in a rational way and seeing if you can explain how it, not necessarily how it, but some idea that you can reproduce this, therefore there must be some mechanism, some way that these things can do. I think I better wrap up there before I go on much. Just to say, I mentioned that there are many references in antiquity to such things. These are just a whole load of references. You're not meant to read them, just be impressed, of literature sources during that period that mention something like an Antikythera mechanism. I'll just show two and then I'll finish. For example, Cicero, the great Roman orator, in his De Naturae, the nature of the gods. The orrery recently constructed by our friend Posidonius, he's writing this about, he'd seen, this is 77 BC-ish, 70 BC, he'd been in Rhodes. Posidonius, in which each revolution reproduces the motion of the sun, moon, and the 5 planets that take place in the heavens every day and night. He'd seen one like this. Not this one, but something like it. Good. And Galen, the great medic of classical times, as you see, this is about 170 AD, he talks about the body, and he's saying, look, the way the body works isn't like these astronomical machines you have that show how the planets go around. So he knows about these. He's a doctor, but he knows that they have these mechanisms that display what's going on in the sky. If I had more time, I'd have gone on. I'll stop here to develop this and say, well, what happened to this? It died out 500, beyond 500, there's not a lot of this in literature, and the Dark Ages have come. But once you get back to about 1100 AD, but that's a whole millennium later, you start getting clocks, cathedral clocks, monastic clocks, and then astronomical clocks. And you get around 1300, 1350 AD, you get the first mechanism that is more complicated than the Antikythera mechanism, which is the clock, astronomical clock of the Donde in Italy. And you can then look forward to Kepler, who started thinking that the universe looks like a clock, runs by clockwork. Interestingly enough, though, Kepler himself, we know from his letters, knew that the Greeks built this kind of machine. He sketched and designed for machines like it himself. So the knowledge that the Greeks did this did persist. But what happened, whether they, whether any examples existed as long as that, who knows? The problem is these were made of bronze, these things. Bronze was valuable if the thing broke. It's not gold, it's not got diamonds in. They were almost certainly recycled for the bronze, huge bronze recycling in medieval and in classical times. So maybe they didn't, no examples will have existed probably to the Renaissance, but the knowledge of them did. And we sort of lost that somewhere along the way. But it's fascinating now that we can see this thing again and know that this mechanism is very complicated. It's very cleverly put together. It's brilliant. And we're confident that it was made when it was made. The evidence is overwhelming that we've placed it correctly in history and when it was made and so on. And I think it's rather a remarkable thing and a great tribute, I suppose, to the Greek state at that time. I'm around for the next day, for this afternoon and tomorrow. So if anybody wants to buttonhole me and talk about other aspects, I haven't had a lot of time to go into everything here. I'll be very happy to talk to anybody over the next day and a half. Thank you very much.
Thank you very much, Professor Edmund.
Hello.
And now the talk is open for questions. Pepe, please, you can manage the questions over there.
Hello, thank you so much for the talk. I was just wondering if this had if people were using it to predict the sky.
Okay, the question they've been asked is what was this used for? I think is what. Now the problem is we don't really know. As I say, it had this instruction book. It didn't say, welcome to your new Antikythera mechanism, which you will use to do the following things. The things it could have been is, it could have been a calculator for an astronomer, but it's not that accurate. As I say, for the planets and for the moon, sun and moon, it wouldn't be that accurate. You'd do better by doing the calculations yourself. So it's not probably a sort of a thing an astronomer would use for accurate calculation. An astrologer, however, might have found this very useful for impressing clients, and they might not worry too much about whether it was accurate or not. He probably wouldn't mention that. But that's speculation. It could have been a teaching device to show you, about cosmic cycles and so on. One which I quite like is that it's a statement. It's if you like, it's a hardwired publication. This is what we know about the universe now. And if you're an intellectual or around that time, you might like to, well, even if you're not a businessman, a rich merchant, you'd like to have that on your mantelpiece to say to all your friends, look how much interest I take in the world. Isn't this wonderful? And there was a sort of thing at that time, I believe, philosophically, that if you contemplate the infinite, it helps you. You become infinite in some sense yourself. It's a good thing to do. So you're all going to become infinite if you keep thinking about infinity. So it could have been that sort of status object. It could have been something you have in a temple, I suppose, if you want to roughly predict what's going on. We really don't know.
You could actually put
Yes, exactly. Yeah, exactly. I don't think you'd have had it on your desk and turned it a little bit every day, because it's going to take 19 years before you've gone around the top, and you've got to go twice more before you reach so it might be a bit boring just doing that. What I think you did was, you're absolutely right, you played with it. You said, well, I wonder what's going to happen next year. I wonder when the new moon, when would we have that birthday party at the new moon? I'll look back, and you could then look and see forwards and backwards. which is, of course, if you were aware of the sky, which of course they would have been much more aware than we are of the nightly movements, might have been a very appealing thing to do.
Question? Enrique.
Yeah, great talk, Mike. Thank you very much. Not much time after the shipwreck, Roman Empire adopted the Julian calendar. I don't know if to what extent this would impact on the fact that the machine was not later reproduced to the new calendar.
Yeah. And the calendars varied so much anyway when this was done. You could easily, I assume, I haven't really thought about this, it's a good question. You could easily make a version that did Julian calendar, I guess. You could alter things if you wanted to a little bit to do that, but you don't really need to, because you can adjust the front calendar ring for leap years and things like that. So all you're really interested in is what the celestial phenomena are doing. And the Julian calendar doesn't tell you anything about celestial phenomena, it just tells what we've adopted as what days are going to be what. So I don't think it would have had a big impact. You could easily, it would still translate, if you like, to being used in the time when you're using the Julian rather than any other calendar. Because when it was first produced, any city might well have had a different calendar, so you'd have had to adapt to that anyway. And the actual one here, the names of the months on the calendar on this thing, in fact, correspond to a region of northwest Greece, which is interesting. So it might have been made for northwest Greece with that idea. But it wouldn't have been too difficult to then take that forward and use it in a different calendar zone.
Isabel.
Yeah. So
To repeat it.
Okay, so the question concerns the unicity of the thing. So it's really unique. So
Yeah.
there's no other similar.
The question is it really unique? Are there any other similar objects? The answer is no. The only thing we have not comparable, but sort of related, is a Byzantine sundial from about 500 AD, which has got about 3 or 4 gears in, but is nowhere near anything like as sophisticated as this. As I say, that the problem with this thing is that this was found because it was in a shipwreck, and it had survived because it was in the shipwreck. Otherwise, these things would break and they'd have been melted down, is what I would guess. I'm hopeful that one day another one will be found, whether in some museum store where people haven't recognized what it is, or at somewhere like Pompeii or Herculaneum, where they're doing a dig, where there's been some sudden event that's terminated things. Yeah, and perhaps, you know.
Is there any other case of some, an object which is unique and found and we do know or do not know what it was?
Gosh, I don't know. I suspect there must be, but I don't know about them.
Because there are many things in bronze.
Yes, yeah, and those wonderful bronzes you see, the statues, a lot of those come from shipwrecks.
Okay.
Not because they were preferentially mounted on ships, because that's where they survived.
Yeah, I haven't been beside
Yeah,
that.
yeah.
There is one question in Zoom.
One question in Zoom. Can I be told it?
René.
Yes, there is a question on Zoom. Sturgis.
Yes, thank you for the talk. I just want to ask quickly, but partially you answered my question, is what is the main unknown from this device? Like, do we know fully how it works, or what is the main?
Yeah, okay, it's a good question. What is the main unknown at the moment? I think that the two things particularly. We know how what we've got left works quite well. We're pretty sure about that. What we don't know is what the planetary mechanism would have been like, and in detail. Though we think there was one, but we don't know what it would have been like and what actually happened to it, whether it bust and was removed or whether it fell off in the shipwreck or whatever. So that's one unknown. The second unknown, I think, was already been touched on in one of the excellent questions, which is, what was this really used for? Why did you have this? The answer to that may just be, well, there was lots of things. These presumably were commercially sold. And if they had several uses, then presumably that helps sales. But we don't really know exactly why these were built. And it would be nice to have some reference that would tell us that. But then again, it might tell us one use, and maybe it was used for other things, but we wouldn't know that. So that's a bit of an unknown as to why they built these particular things. They're lovely, they're great, and I wouldn't discourage them being made.
Yeah.
Should be extremely expensive
The question is another good one, which is, was this extremely expensive? Now, I've thought about this, and I think the answer to this is, it is expensive, but it's not very expensive. It's not made in gold, and it doesn't have precious stones. It might have had some semi-precious stones just to show the planets, but those are being cheap. So, but there's quite a lot of workmanship in that. I know, if you're set up for doing this, I think it's about 2 weeks full work for a couple of people to maybe do this thing. Okay, so it is expensive, but not very expensive. If you like it, it's not a Volkswagen Beetle, and it's not a Rolls Royce. It's probably a lower range BMW.
So it's, the size wasn't very big. Was it something like I mean,
shoebox?
So that's they made it just.
Yeah, it's portable. It's portable. That's the thing. You can carry it around with
like
you.
Our devices here, like a phone, something like that.
Yeah.
So I have a question concerning the text, because you make reference to Greek text.
Yes,
right?
and Latin text.
And Latin. So the Romans already knew that, and then there's a big gap with the next ones.
Yeah, well, there's a gap beyond about 500 AD to maybe 1100 AD-ish, something like that. So there's that gap. But there are some Arabic sources which do talk about various mechanisms, but there's nothing quite like the Antikythera Mechanism, although there is and I've got a picture, but I haven't got time to show it now, of a astrolabe in Oxford, which is from around 1100 AD, which has about 5 or 6 gears in, but has a nice little display which shows the sun and the moon, sort of to show lunar months. It's not very accurate, but it does have a display like that. So, but that's one geared astrolabe. Most astrolabes weren't geared and didn't have that in. And I don't know of any proper good Arabic account of something like the Antikythera Mechanism. Doesn't mean there isn't one, because a lot of Arabic sources haven't been properly investigated yet. You have to speak Arabic to start doing that. And I'm afraid, don't think I'm going to be able to learn Arabic. That'll have to be in my next incarnation.
So,
I don't know what's the material to make this kind of stuff. It's copper or?
It's bronze. Bronze. Yeah.
And is that use some oil inside?
Yeah, it's bronze. I think the shaft, some of the shafts, I'm not positive about this. I remember reading this. It needs redoing. Is some of the shafts are sort of primitive kind of steel, okay, which they did make primitive kind of steel. And there's some evidence of little holes that might have olive oil would have been probably the thing you would have used to lubricate it. Yeah, but it's so, there's no way we could find traces of olive oil in it after it's been under the sea so long and so on. But the teeth are just filed with a file. You can make file. If you're interested in this, there is a very lovely series of videos on YouTube of an Australian guy who is reconstructing a model of the thing, and it's all his workshop techniques as to how he does it. And it's fascinating because he tries techniques that would have been available to them. He actually makes the files to show how they could have made the files to do the teeth and so on. And it does work. If you make a reconstruction with gears with his teeth, it does turn, but it's a bit clunky. It's not like modern gears. It's a bit clunky, but it does work.
So you have one of your last slides, I think you were trying to link with the philosophical framework.
Yes.
That what you say is,
yeah,
the knowledge of this mechanism,
yeah,
make a framework, or philosophy say that
yeah,
there's a scientific view of the world, a scientific view of the cosmos.
Yeah.
So these people were thinking in a different way than the.
Yeah. These are all the slides I would have shown. There we are. Wikipedia. Here you are. Can you read this? Yes. Wikipedia. The mechanical philosophy is a term that after the scientific revolution of early modern Europe, in which an innovative branch of natural philosophy arose during a period of 16th, this is AD, describing the universe as similar to a large-scale mechanism. The Greeks got there first by a long way. Yeah. But I think it's interesting, if they did this, and there have been suggestions that in fact some of the mathematical advances they made might have been stimulated by looking at geared mechanisms, and thinking about the ways gears interact. It's pure speculation, but it's a very interesting idea that there perhaps may have been some interaction between the actual astronomical theory and these mechanisms. And I certainly think philosophically it's very important, because you see this thing, you can see it moving like the universe, you must make you think, does the universe work like this or how?
That remember me, I think hope I'm not wrong, but there, I think there were some before, probably the 14th century, there were some philosophers. I think Raimundo, maybe they have this kind of mechanical, philosophical, like syllogism. They have also this kind of mechanical
devices. Yeah,
devices
yeah.
To make logic.
Yeah, well, I mean, during the 18th, 19th century, here, so you know, they loved them. The 19th century,
even in the logic
yeah.
elements.
Yeah. Okay.
Thank you. Thank you, Mike. What to do, we can meet the